Hello, this is Che from Northeastern University, and this is part three of the series on spectral clustering. So, in part two, we were going over eigenvalues and eigenvectors. Of course, I was too lazy to teach it because I realized there are a lot of good materials out there already. So, I provided some links to other videos. And if you go over them, you should have a very, very good idea of both eigenvalues and eigenvectors. Now, today, instead, I'm going to move on to something that's not taught very often because sometimes, or often, people just assume it's really obvious, but it wasn't that obvious to me. So I'm going to go over it anyways. And that is, how do you find a derivative of this right here, where x is a vector, a is a matrix, and x is a vector again. So what this means is this right here. You have a here, and then xAx. Now, this is something, the multiplication part is something that you should have learned in linear algebra. But the calculus part of how to take derivative of this, it's not always that clear. So at least not to me. So I'm going to go over it. And so, of course, this x right now is 3-dimension. It could be 4 or 5. This could be however long. The higher dimension, the more it goes. And this is always a square matrix. And this will just keep getting bigger and bigger. And this will keep getting longer the higher dimension you go. But to demonstrate the point today, instead of having very high dimensions, why don't we just do a very low dimension one? And you should be able to apply the same ideas to higher dimensions. And the idea is really simple. You just multiply them out, right? So it will look like this: a11 x1 plus a12 x2, and then 2a21 x1 plus a22 x2. So the first thing I did is I multiplied them together. Okay, now let's multiply these two together. So this one multiply this, a11 x1 squared plus a12 x1 x2, and then this one multiplies this plus a21 x1 x2 plus a22 x2 squared. Okay, so now you want to apply this x1 x2, and what this right here means, just a matter of notation, is like this. I wonder if I can just copy this. Let's try copy, paste. Oh, here it is. So yeah, let's see if I can paste again. There we go. So when you take the derivative, what it means is, you see, it's a vector. So you will do partial x1, partial x2. That's all that means. And now we just take the derivative of this thing with respect to x1, and this one with respect to x2. So let's do that. And that will give us 2a11 x1 plus a12 x2 plus a21 x2. And this one right here, there's no x1, so it's a constant, and therefore it's just equal to 0. Now let's do the bottom one. Bottom one, this one cancels out. We have a12 x1 plus a21 x1 plus 2a22 x2. Okay, and that's our solution. It is that simple. Of course, you don't want to do this every single time. It gets very painful, especially if this becomes like really, really big, right? So maybe there's a trick to it. And the reason why I start off by doing doing it this way is because I want to show you how the trick works. So now let's notice how this right here is x1, right here is x2. So we could actually do this. To remove x2, remove x1, and then remove this, and then combine these two together. Okay, x1, x2. That was the same thing that we just got. I essentially, I did that wrong. A1, 2, what's this? There we go. This is basically, if we were to actually multiply this here out, you will see that it's the same thing. Now, I'm going to further divide this up, okay, into this. A11, A12, A21, A22, plus A11, A12, A21, A22, X1, X2. Okay, notice how if I add this and this is 2A1, A12, A21, A12, A21. So I just separated them out. Now, what is this? Well, this is X. This is this thing right here. And what is A? A is right here. A11, A12, A21, A22. So this right here is A. And what is this? Well, it's A11, A21 instead of 12. And this is 12 instead of 21. So this is switched. And therefore, this is A transpose. So what I'm saying is that the derivative of X, this expression here, you don't have to go and multiply every one of them together. And of course, if dimension gets really large, it will take a really long time. So what you could do is just realize this relationship. A plus A transpose times X. That's it. Like from this, you can jump to this automatically. Now, there's a trick, right? There's another trick. This is for all cases. But what if for very, very special case where A is equal to A transpose? What I mean is, like right now is A12. What if that is equal to A21? So we're talking about like a symmetric matrix where you have like 1, 2, 2, 3. So if you find a transpose of that, it'll be 1, 2, 2, 3. So if they're symmetric, what does that mean? Well, it means this right here. 2A11 and then 2A12, 2A21, 2A22, X1, X2. Do you see that? Here's the 2, so they don't change. But if they are the same, it's the same as just adding 2 here and cancel that out. Now, this is an even easier form, right? So this is not symmetric. But if it's symmetric, this right here is equal to 2AX. Now, this you can draw quite a bit of parallel if we have like 3x squared, right? If we want to take the derivative, that's the same as 2 times 3 times x. Now, this right here, xAx, it's also square because there are two of them. If you were to take the derivative of this, it is 2 times a times x. So what do you know? 2 and x, 2 and x. And then the middle value is this a. So this is a good way of remembering how to take the derivative in terms of matrices because it looks very, very similar to just regular derivative. Of course, there different people represent it differently. Sometimes some people would do x transpose a, but that's actually the same thing, except the whole thing is transposed. It depends on how you like to represent it, but you just need to keep that in mind. This is the same. So this is how you take the derivative of this. Okay, and that's it. In the next video, we'll go over something else. Okay, thanks. Bye-bye.